Assalamu alaikum wa rahmatullah.
عليكم السلام.
Yeah, I heard. All right. Last week I had some issue with my system. I couldn't, although it is, I mean, all over the campus. I think that day lectures on Blackboard were difficult. I mean, people were not able to conduct their lectures on that day. So I needed to install another program later, Firefox. Um, I will make up the class that I missed last week. I will record it. Probably maybe on Wednesday. I will schedule it. So anyone that wants to join can join if he's free. Okay. Otherwise, the recorded session will be available on Blackboard, so you can watch it. You have to watch it because it's for a missed class. You have to watch it. I will not. I will only like maybe after that take questions if you have any. Maybe during the class. Okay, but I will let you know when I will prepare. I will make up the lecture so that those of you that may be available, you can be with me during the time that will be. I will schedule it like a normal class and then present it, and then after that, the Blackboard will automatically create the video recording of the class so that you have to watch and then follow up on that. Okay. So now we will continue from where it's, oh, someone is asking how much. Yeah, I'm fine, I'm done. How are you? I hope you are preparing for the major exam, okay, which is now week 6 and 7. We're waiting for the confirmed schedule of the major exams now so that we can distribute to you, okay? So we will continue from where we stopped. We're discussing runoff. Let me take the presentation mode. We're discussing the Horton's model. Okay, we discussed this. Discuss this one as well. Okay, we're discussing the Horton's model, which shows the infiltration capacity P, which is given by the, if you know this formula, F naught, initial infiltration capacity, FC, final or constant infiltration capacity, okay, which is equal to the apparent rated conductivity or hydraulic conductivity, okay? We said the hydraulic conductivity is the ease with which water flows through the soil, okay? The ease, that is how simple is it for water to pass through the soil. The plot of the Horton's equation is an asymptotic curve that starts at F naught. This is F naught, okay, which is the initial infiltration capacity. And then when you have rainfall, that infiltration capacity reduces to a constant. You can see it dropping, okay, up to when it becomes constant, where you have FC, which is final or constant infiltration capacity. So because at the beginning you have voids, that water can seep into, can fill those voids and displace the air inside. But over time, such voids become filled with water, and then there will be no vacancy, there will be no space for water to fill into, okay? And then the infiltration capacity becomes constant in that case, so it can no longer penetrate the soil, okay? And then the portion of the precipitation intensity above this infiltration capacity time curve during different time intervals is designate the runoff and depression storage. So this is the portion for the rainfall intensity. Okay, the rainfall is on the average probably occurring at some, the same time, some intensity, it falls, it increases. Okay, so this is the rainfall intensity of time. Okay, and this is the and then above here we are saying that the portion of the precipitation intensity above this curve designates the runoff and the depression storage. Okay, so this curve we have the runoff. Okay, we have the runoff. So this is the rainfall intensity. This is the revised infiltration curve, the original infiltration capacity. We will explain. We will come back to this curve again. So don't worry. We'll come back to it and take each of these items bit by bit. The revised storm. You remember we said rainfall. We call it precipitation. At the same time, we call rainfall storm. Okay, when we say storm, precipitation, rainfall, we are referring to one and the same thing. Okay. So at the beginning of a storm, if the precipitation for a certain duration occurs at a rate less than the infiltration capacity, okay, you have precipitation, that's rainfall, at a rate less than the infiltration capacity, that is the capacity of the soil to absorb water, okay? The soil moisture deficiency exists and the capacity for infiltration remains high at point C, okay? The capacity for infiltration remains higher at point C in the previous figure rather than falling point B, okay? We are still explaining the curve, okay? At the beginning, if the rainfall intensity is less than the infiltration capacity, okay, there's soil moisture deficiency because the soil can still absorb more water. So, okay, so that is what it means. The soil can still absorb more water, and the capacity for infiltration remains higher. So, meaning the soil can still take more water. So, if it can still take place. Okay, so rather than falling to point B, because of the intensity that we have, so it remains at point C. Okay, because don't forget fall. Okay, this is the rainfall intensity. Now, for calculating runoff, okay, if there is any depression storage, depression storage is simply water that accumulates on the surface. That's simple. Okay, that is the depression storage. Depression, that's when you have like an undulation, like a basin, something where water accumulates. That's depression. Okay, so that is the simple definition here. So the depression storage capacity S, and this depression storage is accounted for first until S is completely full. What are we saying here? Let me take it again. For calculating runoff, you see, when rain falls, it first seeps into the ground, it infiltrates before it starts to run off, or before you begin to have runoff flow. Okay, there should be some level of saturation of the soil before it begins to flow above the soil. Flowing above the soil, that is runoff. Or accumulating above the soil, that is depression storage. So what we're saying for calculating runoff, if there is any depression capacity, S, depression storage is accounted for first until S is completely full. So until that depression is filled up. For each time interval, the depression storage, delta S, is the minimum of the following two values. So for each time interval, the depression storage, okay, is the minimum of the following values. The first one is saying delta S equal I delta T minus delta F, okay? What are all these terms? I delta T is the rainfall intensity. I is the rainfall intensity. Delta T, that is because it is expressed usually in per time. So when you multiply with the time, you have it in depth only. And then you have delta F. Delta F is the accumulated infiltration. accumulated infiltration. We will go and explain how to find it, okay? Don't worry. So what we are saying is that the depression, this formula, what is it telling us? The depression storage is difference between, the rainfall and what has infiltrated. So the remaining balance will now fill the depression. Okay, you have the first item is rainfall. This is the rainfall. Okay, so when you take away the cumulated infiltration, that is the water that has infiltrated into the soil, when you take away that amount from rainfall, the remaining will fill the depressions, will form the depression storage. Very simple. Okay, and this is the other formula for finding the depression storage, which is depression storage capacity minus the storage from previous step. So minimum of these two equations is what we use in determining the depression storage. Okay, like I said, we are going to apply this formula. Okay? So don't worry, we'll have an example in 3 minutes where we'll demonstrate the use of this equation. So after S is computed, the runoff is calculated. You remember in the first point here, the first point I said for calculating runoff, if there is any depression storage S, depression storage is accounted for first until S is completely full. That is if it exists, because the ground surface may be such that you don't have any depression storage. There is no, will I say, basin like. There is no, will I say, hole that will hold the water. So water will just flow on the surface of the water, and that will constitute our runoff. So if you don't have any depression storage, then once you have the water becoming, the soil becoming saturated, water will just flow. So you will have runoff. But if you have depression storage, before you have runoff, you must have depression storage. What are we saying? Let's say, let me demonstrate. Let's say you have it this way. It rains, okay? So it seep into the ground, it infiltrates. If infiltration capacity, has been reached, when it reaches the maximum infiltration capacity, then water will begin to flow, isn't it? A runoff. Now, what happens? But if you have some depressions, let's say you have the surface is something like this, and then like this. So what happens is when water falls, it will infiltrate into the soil below the depression. Then if the infiltration capacity is reached, then water will accumulate within the depression. Okay, it will accumulate within the depression until that depression storage is full. Until it is full. If the depression is filled up, the remaining water will now flow. Okay, it will now constitute our surface runoff. Is that clear? But if you don't have, in this case, you have depression storage. In this case, the depression storage is zero. So you don't have any depression storage. So what the first statement is saying is that if you have depression storage, so you have to account for depression storage until it is completely full. Like in this case, it has to be filled up before you begin to have runoff. So what this equation is telling you is that runoff is what? Is simply the rainfall, the rain that falls. When rain falls, because that is our main input into the system. Okay, that's our main input in this case. Rainfall, precipitation. Part of that will infiltrate, will form the cumulated infiltration, isn't it? And if there is depression storage, part of it will form delta S. And then until these are filled up, okay, then you begin to have the balance will now form runoff, okay? The balance will now form runoff. So that's why you have delta F here, delta S here. So when you take away delta F and delta S from the rainfall, the balance will now give you runoff. Is it clear? I enabled your mic so you can talk, okay? So now we will, like I said, we will take an example where we will demonstrate this, okay? Now, where R is the runoff and delta F is the difference in accumulated infiltration F during time interval, and delta S is the change in depression storage during delta T. Now, I need you to give let me check what you are, because I was using the presentation mode. Okay, saying K, is it constant? Okay, let me go back to the slide. Okay. What is K? K is a factor representing the rate of decrease in the capacity, and its unit is per time. Yes, K is a constant. Okay, F naught and K have no physical basis. Okay, they cannot be determined from soil water property and must be ascertained from experimental data. Okay, so K is a constant value that has to be ascertained from experimental data. Okay, so now let me move to the, okay, example. So what we are saying is, when rain falls, first, if the rainfall intensity is less than the infiltration capacity, rain seeps into the ground, it infiltrates, okay? And then when the maximum infiltration capacity or the constant infiltration capacity is reached, then it fills depression storage if there is any. If there is no depression storage, it overflows. It flows on the surface as surface runoff. Okay, so now this example will take you through. It says we have the infiltration capacity curve for a watershed is given by, I told you, watershed, catchment, basin, they all refer to the same thing. Although sometimes, just now, when I mention basin, I mean just like a container, like some kind of a hole in the ground can hold water. Okay, but by and large, basin, okay, refers to an entire area, a large aerial extent. Okay, let's say the whole of Hafrul Batin can be referred to as Hafrul Batin Basin, or Hafrul Batin catchment, or Hafrul Batin watershed. Okay, so it's a large area that has one outlet. Okay, whole water falling as precipitation area will go out. Okay, will go out through, let's say it is Hafrul Batin. Okay, you may have a main channel. Okay, when rain falls, you may have small channels feeding into the main channel. Okay, feeding into the main channel. You may have smaller ones, evaporating water, run out. Okay, so you can have primary channels, secondary channel, tertiary channel. So all this, but at the end, it has one outlet. The whole water will go out through one outlet. Okay, that is the basin outlet. Okay, so this can be like a representative of the whole Hafrul Batin city. Okay, so we call it watershed, we call it catchment, we call it basin. Is it clear? So here it says the infiltration capacity curve for a watershed is given by FP equal this. Okay, remember in the formula here we have naught minus FC, and then here we have FC. So in this case, FC is equal to 0.83 and F naught is 11.66. F naught is the initial infiltration capacity, and then FC is final or constant infiltration capacity. Because when it falls, it will ultimately reach the final infiltration capacity over time. Okay, so this is the infiltration capacity curve, okay, given by this, where T is in minute and LP is in inch per hour. The storm pattern is provided in the table below. So this is the table for the storm pattern, time, interval, and the intensity. So you can see intensity increases and then decreases over time. 0 to 10 minutes, you have 3.5 inch per hour, and then it increases to 3, 8, then it started decreasing. 5, 1.5, increases a little bit, okay? And this is like the usual and the practical form of rainfall, okay? It doesn't fall at the same intensity over time. So the intensity dwindles or it fluctuates, okay? So here what the question is asking us is to determine the rainfall excess. Remember, we call runoff as also rainfall excess. Okay, it's another term that we use in describing to describe runoff. Okay, so determine rainfall excess for the successive 10-minute period. You can see the time interval here. Each is 10 minutes, 10 minutes, 10, 20, 20 to 30, like that, up to the 60th minute. We are to determine the rainfall excess using the infiltration capacity curve as well as the rainfall, the storm pattern. Okay, so solution here, the infiltration capacity is computed in column 2 of table 4.1 at various times by the given formula. Okay, so here we come here, and what do we do? You see here K is already provided. K is 0.07. Did you see K here? So the only unknown here is T, which is the time. So we use the time provided here we just substitute the time to find the filtration capacity at different time interval. Okay, at different time interval. So this is the infiltration capacity and cumulated infiltration. We divided the time from 0, the interval is 10, so 0 to 70. You can see 0 to 70, and then we just here we just use the formula and just substitute, plug in the value of T, because the only unknown in the formula of the filtration capacity curve is T. When T equals 0, it means the initial infiltration, so definitely we will have 11.66, and then when T equals 10, we will have this. Is it clear? And then from there we have delta T, okay, which is the successive difference in column 1. Okay, delta T, the time interval, and it's the same throughout, because the difference is 10 minutes for each interval. Okay, so now what is average infiltration capacity? So here the average infiltration capacity, we have B, average of 2 successive values of column 2. We go to column 2, so average of 2 successive values. So 11.66 plus 6.21 over 2. Okay, so when you have this, you will get that value. Okay, this one and this one, the average will give you this. Okay, this one and this one will give you that. Okay, like that. Okay, this, and then the average infiltration capacity. This one, you have this. Okay, and look at the way it is placed. Okay, now from there we now try to find the cumulated infiltration. Okay, and how do we find the cumulated infiltration? The average infiltration capacity in terms of inch per hour. So we multiply by the interval. So this is 10 minutes. We convert it to hour. Okay, that's C. So column 3 times column 4 times 1 over 60. So we are just converting the unit. Okay, you have inch per hour, and you are multiplying this with minute. So how do you convert it? Okay, 1 minute. 1 minute is 1 over 60. Okay, so for 1 hour gives a minute. So in this case, hour will cancel and minute will cancel. Okay, so you now multiply column 3, the time interval will column 4, and then divide by 60, get column 5. Okay, right? And this is also explained here. You can see column 3 times column 4 times O divided by 60. Okay, so this will reduce this from inch per hour to just inch. Okay, so here we'll have inch. That's the depth of water that has infiltrated. Okay, that's the cumulated infiltration. Okay, so that is how we obtain each of these. Like this one, it will be simply 10 times 8.94, which is 89.4, then divided by 60. Okay, that will give you 1.49. Okay, so it's going to be 8 times 9.4 times 10 over 60. Okay, so 1.49. Okay, and then being the first value, this is the cumulative infiltration delta F, and then FD is the accumulation of column 5. So this is the first value, so we just transfer it here. Now,
Doctor, excuse me.
yes.
I think the screen you're sharing is only stuck on slide 14. We can see
What?
the other slides. The screen is stuck on slide 13. 14. I mean.
Slide. Okay, let me.
Yeah.
I am on slide which
Now
15.
it's 15. Yeah. It was stuck on 14. But now it's
Okay, then.
yeah.
Okay, let me. Sure. Okay. But can you see it now? Can you see slide 15?
We can see it now.
Okay. Okay, then let me go over the explanation briefly again. So, meaning all the explanation you did not see the slide. Okay, but I already uploaded the presentation. Okay, so you can download it from Blackboard and then open it. Okay.
Okay.
Yeah. But I'm sure now it's clear, so you can all see it. Right?
Yeah, we can see it.
Okay. So let me briefly take you over it again. You know, this is the time interval, the time duration. FP, we use the formula and substitute T, okay, to get the column 2. Column 3, the difference between the successive time intervals, which is constant, 10. Column 4 is the average of the infiltration capacity. So average of this and that, we get this. Average of this value and value, we get this, okay, like that. And then column 5, which is the cumulated infiltration, the change in the cumulated infiltration, we try to convert from to convert the infiltration capacity from inch per hour to just inch by multiplying with the time interval. Simple. And this is in minute, this is in hour. So we have to divide by 60. Inch per hour times minute. So we have to times 1 hour over is give 60 minutes. So at the end we will have our cumulative infiltration in inch. So that's how we got this column 5. It's also explained here. You can see that. And then the last column is the accumulation of column 5. So the first one here 1.49. So we added it to this one. 1.49 plus this will give this. Then this one plus this value will give us this. Okay, like that. So okay. So that is the accumulation of column 5. Okay. Now, if you look at the rainfall intensity table, the first table provided, during the first table provided on slide 14. If you look at this table, okay, during the first 20 minutes, rainfall intensity is less than the infiltration capacity. Hence, all rainfall is infiltrated. Okay. The first 20 minutes, you can see infiltration capacity. Okay, 11.6, 6.3.5. Okay, the minimum is 3.5. While the rainfall intensity for the first 20 minutes, the rainfall intensity, the first one is 3.5 and then 3. Okay, 3.5 and then 0 to 10 minutes is 3.5. So 0 to 10 minutes is 3.5. Rainfall intensity is less than the infiltration capacity. So all rainfall will be infiltrated because it is the infiltration capacity has not been reached. Okay, at that point. And then you move to 0 to 10, and then 20, 10 to 20 is 3. So 3 is the rainfall intensity, while the infiltration capacity is 3.5. So the soil at this point has the capacity to take or to accept all the infiltrated water. What about at the 38th minute? Here you have the rainfall intensity 20 to 30 minutes, you have inch per hour. 8 inch per hour, and infiltration capacity has started reducing here to 2. So the infiltration capacity has started reducing. So now it is 2, while the rainfall intensity is, so it is greater than the infiltration capacity. Okay, so what are we saying? Here, the 0 to 10 minutes, you have the rainfall intensity to be 3.5. And then 10 to 20, you have the rainfall intensity to be 3 inch per hour. And then 20 to 30, you have the rainfall intensity to be 8 inch per hour. Okay, so let's examine it again. 3.0 to 10 minutes, the intensity of rain is 3.5 inch per hour. Filtration capacity initially is 11, we have started reducing to 6.2. So it means the soil has the capacity to accept all the rainfall, so there is no runoff in that case. Okay, now 10 to 20, the same thing. The rainfall intensity is less than the infiltration capacity. Then 20 to 30, that is when the rainfall intensity has increased beyond the infiltration capacity of the soil, because of course as it rains, the infiltration capacity keeps on reducing because soil is absorbing, is accepting water, so its capacity reduces. So that's why you can see it is highest at the beginning, 0 minute, okay, and lowest at the 70th minute. Okay, so what are we saying here? Let's go back. So during the first 20 minutes, the rainfall intensity is less than filtration capacity. Hence, all rainfall is infiltrated. So all rainfall is infiltrated. So how do we determine the amount of rainfall during the 20 minutes? The rainfall intensity is 3.5 and 3 in inch per hour. In inch per hour. So now we have to now convert it to 9 inch. Okay, this is in inch per hour. And during the first 20 minutes, this is the first 10 minutes. So the first 10 minutes, you have 3.5. So times 10, okay, times 10, but that is a minute. So we have to convert the minute to hour. So that's why we are dividing by this 60. Okay, during the second 10 minutes, this is the rainfall intensity times 10, which is interval, okay, then divided by 60, okay, and then we have the total rainfall infiltrated as 1.06. Let me check what 18. Okay. Teacher, how can you find delta F? Okay. Delta F is simply found by multiplying column 3 and 4. You multiply, you have column 4 that has the infiltration capacity in inch per hour, and you have column 3 that has the rainfall interval in minute. So you just multiply them out, but you have minute and hour, so you have to convert. So that's why we divide by 60. Okay, so that is how to find column. Okay, good. Then let me go back to the slide again. Go back to the presentation mode. All right. So this is the total rainfall that infiltrated during the first 20 minutes. Okay. Now we now prepare a revised infiltration curve. Okay, a revised infiltration curve. Now the revised infiltration curve here, this is the infiltration capacity FP, which we already determined, in column 2 of the previous table, and then this is F, which we determine at the end. Okay, this is F that we determined at the end. That is the cumulated infiltration. Okay. So, it begins, this value, we know is about 11.66, and then the infiltration capacity reduces, okay, or time reduces, okay, and this is the accumulated infiltration, which is the final value of 0.16, okay, 0.16, let me check, okay, 6.21. 1.5. Okay. So this is a plot between the, if you look at table 4.1, between column 2 versus column 6. Okay? Column 2 versus column 6. Column 2 is the infiltration capacity, and then column 6 is the accumulated infiltration. Okay? Is accumulated infiltration. So at this point, where do we have 1.08? This is 1.08. Okay, inch, which is an inch. So when we take it up, we want to find the infiltration capacity at that point. Okay, and this is 7.5. So the infiltration capacity for the at this point is 7.5. Okay. Now we now take 7.5 as the initial value of F naught, or the initial infiltration capacity at 20 minutes. Okay, from this point onward, the total infiltration curve is given by, we now revise up. Remember, initially here we have 11.66, which is the initial infiltration capacity. But we now realize that until after the first 20 minutes, all you have is infiltration. So water has accumulated. So we now revise, this is the equivalent initial infiltration now. That is when you have the rainfall intensity being greater than the infiltration capacity, being greater than the infiltration capacity. So from this onward, all we did to review this, and we use prime, okay, which is for the revised infiltration capacity, okay, where T prime, also here we use T prime, is the time counted 20 minutes after the start of the storm, because at the beginning all the storm is infiltrated into the soil until after the 20th minute. That is when the intensity of the rainfall becomes less than the infiltration capacity. No, not less than, but becomes higher than the infiltration capacity. Okay, so using this equation, the revised storm infiltration capacity at different times is calculated and plotted. Okay, this is T prime. T prime is now counted 20 minutes after the start of the storm. Okay, 20 minute revised infiltration capacity for the storm. So this is 0, 10, 20. So instead of 70 here, we will have 50. Because counting 20 minutes later. Let me see what you are saying. So the curve depends on column 2 and 6. Yes, it depends on column 2 and 6. You are right. And then teacher, may you use the mouse sign, please. Mouse sign. What's mouse sign? I'm using my pen to write on it. I'm done. Hamdan, can you talk? Because I use it in the presentation mode so that I can, write and show a lot of, things, draw and sketch. Okay. So now, based on this formula, we prepare this one, okay, using T prime. So we now use T here, okay, and then we use the revised initial infiltration, okay. And now this is what we have. This is the rainfall intensity from the table given in slide number 14. Okay, it is plotted. This is the rainfall intensity. Okay, and this is the revised infiltration curve, revised storm infiltration curve. Revised storm infiltration curve. Because after 20 minutes, at the beginning, all water is infiltrated, okay, because of the fact that the rainfall intensity is less than the infiltration capacity, okay, so all water is infiltrated until after the 20th minute. That is when the rainfall intensity becomes greater than the infiltration capacity, and that is when you will be to have partly will be infiltrated and partly will fill the depression storage or becomes runoff. So from here, you now have the revised infiltration curve, and this is the original infiltration capacity curve. Okay, and then later I'm going to explain this dashed point. Okay. Now the computations of rainfall excess, that is the runoff, during different time intervals are arranged in table 4.3. Okay, here we don't have depression storage, so runoff is simply the difference between the storm or the precipitation and the cumulated infiltration. Okay, that is I delta T minus delta F. Okay, so how do we find the rainfall excess or the runoff? Still, column 1, we have our time in minutes, okay, 0 to T, and then we have the revised infiltration capacity, F prime P. The revised one started at after the 20th minute, isn't it? Okay, so here we just put formula and put T equal 20 and determine this. Okay, we already did that. We already did that here, the revised infiltration curve, which is this one, okay, which is this one. So, except that here, the time, this will be corresponding to 30, okay, like that, and this 50 will be corresponding to 70. So, this is FP, okay, and delta T of is the time interval, which is constant in each case. Delta T is 10, and then average infiltration capacity. So usual, we take the average 7.5. No, how do we get this value? This is 7.5 plus 0.14 over 2. Okay, and then the same thing here, 4.4 plus 2.47 over 2. Okay, this one and this one, in a similar way. And then we now get the cumulated infiltration, delta F, okay, by accumulating this, by multiplying with the time interval, okay. But when we multiply with the time interval, we divide by 60 to convert the, hour and minute to make sure it's homogeneous, okay. So that is how we got column 5. And then here we put the rainfall intensity from the 20 to 30 interval, okay? From 20 to 30 interval, we now put it. Because runoff begins after that. That is why we are ignoring the period between 0 to 20 minutes. At that period, because of the fact that the rainfall intensity is less than the infiltration capacity, all water is infiltrated. So there is no rainfall excess, okay? So this is the rainfall intensity from the first table, okay? We just reproduce the value here. From the first table, we didn't do anything. And then how do we get delta P, which is the change in precipitation or the precipitation. Just I, this is I times delta T. Okay, this is I, this is our delta T. Okay, so this will give us the rainfall in inch. Okay, but at the same time, when we do this, we will have to divide by 60 because I is in inch per hour, delta T is in minute. Okay, so this is how we got this column as well. And then the last one is the rainfall runoff, okay, which is the difference between the storm and the accumulated infiltration. Okay, the difference between the storm and the accumulated infiltration. So now, in this case, this will just simply be column 7 minus column 5. Okay, column 7 minus column 5. Negative value, okay, column 7 minus column 5. You see, this is negative, so we cannot have negative runoff. So we strike it to 0, but we carry it over because it has to be compensated. It's like it creates some kind of negative value that has to be filled. Okay, it has to be compensated for. So this negative value is added to the next value. Like this one, this is 0.4 minus 0.24, and then we say plus or minus 0.09. Okay, so this is how we got this. But we shouldn't have any negative value in the runoff. Okay, once you have negative value, you strike it to 0 because it means you don't have runoff during that particular time interval. Okay. Now, still on explaining why we have the negative, during the time interval 40 to 50 minutes, the rainfall amount is less than the cumulated infiltration. The rainfall amount is less than the cumulated infiltration during this period, okay, by 0.09. So rainfall is less than the cumulated infiltration by this amount. So runoff for this period is 0. Okay, it cannot be negative. This is very important. It cannot be negative. Okay, this deficiency of 0.09 is made from the rainfall of the succeeding period. Because of the fact that the rainfall is less than the cumulated infiltration, so it has to be compensated for, and it is compensated by the rainfall of the succeeding period. Okay, which is also shown in the graph here. You can see the revised storm, the revised infiltration curve. Okay, 40 to 60 minutes, you have this deficit. Okay, this is the 0.09, which is compensated for by the next interval, 50 to 60 minutes. Okay, so the same amount is compensated. So that is why we added it to the next next calculation. Okay. Yes, someone is. Let's see. Which graph? Okay, no, I have already shown you the graph. Okay. Yeah, this one. Okay. Now I will give you just about a minute break, and then we come back. We are done with chapter 4. We will now move to chapter 5. Okay. Any question? It was bag 17. It was. Well, what do you mean, Ahmad? Ahmad Abud. It was bag 17. What do you mean? What do you want to say? Ahmad? Okay, then let's take this break. Come back. We move to the next chapter. If you don't have any questions, okay?
Doctor, I mean, you are explaining about the graph in page 20, but it's still on page 17. We didn't say anything. We didn't see it.
But it is showing 20 here. Okay,
But showing to me 17, just 17.
what about now?
Now it is 20.
Okay. So are you the only one? Okay, I think what will happen maybe I will
No,
be I
not
will
just me, Doctor. There's other students.
oh, oh the other students are seeing the slide I was using. Hmm? All right. So just let me know. Oh, what if I move to the next slide? I will tell you so that you follow. And if you are not following, if it doesn't move to the next slide, you now let me know. Okay. All right. So let's take like 5 minutes break. Okay, we're back. Let me share the screen. All right. Now, chapter 5, you see, where we started, chapter 1, we gave general overview of the development of water resources, how to calculate design capacities of the different aspects of water resource development. And then we moved to the hydrologic cycle, where we explained what happened during the hydrologic cycle, the different processes taking place, precipitation, filtration, runoff, groundwater flow, and what have you. So now, like I said, we're taking each of the components of the groundwater cycle, of the water cycle or hydrologic cycle to explain in details, okay? We looked at precipitation, we looked at evapotranspiration, and now when water infiltrates, okay, it percolates, it improves the soil moisture content, and then if it is in such a capacity that it can move deeper down, it moves down to join the groundwater table. Like I said, the groundwater flow is like a river flowing underground, okay? So to join the groundwater table, okay? So now we will look at some simple aspect of the theory of groundwater flow, okay? Like I said, this course is an introductory course to water engineering. It is made up of many specialized courses. So we'll introduce you basically to the most basic concepts here. But then if you feel interested, you can take senior elective courses, you know, like for instance, there is a course in hydrology, okay, which will look at the hydrology part of the groundwater, okay, the precipitation, you know, unit hydrograph and all that. And then there is a course on groundwater hydrology as well. You have groundwater hydrology, which will go into details about the groundwater flow and all that. And then, as we are going to see later, we have another course, you know, in open channel flow, or you know, that's hydraulics. And then you have another one in distribution system. Okay, so what we are doing basically is to introduce you to the basic concepts, you know, so that at the end you have an idea about the water engineering. At the end, if also you develop interest enough, you know, then you can take, you know, some option electives in the CE in those areas. Okay. Now, the theory of groundwater flow. And don't forget, I told you Saudi Arabia it has huge groundwater resources. Okay, most of the water supply for municipal use and irrigation and what have you. I mean, about 50% we use groundwater here, okay? And then the remaining 50% comes from water desalination plants. Although there are plans to reduce the percentage or the usage of the groundwater so as not to not to significantly affect the quality, because over time when you keep on pumping and pumping and pumping, you know, that affects the quality of the groundwater. So in order to avoid that impact on the groundwater, the kingdom is moving away from using the groundwater, you know, to using more of the desalinated water, which is for the ocean. The ocean has enormous capacity, enormous amount of water that is almost inaccessible. So using the desalinated water is another very good option that the kingdom is moving towards. Okay. Now, the intended learning outcomes here, you know, you're able to explain the different subsurface water zones and understand the basics of groundwater flow using Darcy's law. Okay. Yeah, this is just another good picture. You have, you know, rainfall, infiltration, soil moisture, unsaturated or vadose zone, then capillary fringe, saturated zone, you know, what have you. So now we'll take some definitions.
Doctor,
Yes.
I think the thing is doing. I think it's still stuck on the first slide again.
On the first slide, okay, then let me.
It doesn't show the changes we made.
What about now?
It's on slide 3 now.
So it's showing.
For some reason, it doesn't show the changes when you explain, but
Okay, then let me see. What about now? Does it change?
yeah, it changes now.
Okay. So maybe I will stop using the presentation mode, but the presentation mode is so excellent. Otherwise, I may need to upload it. Okay, let me use it this way for now and see. Okay.
Okay.
And not in the presentation mode. So let's take some simple definitions, okay, related to the groundwater flow. So groundwater, which is the water in the zone of saturation. When we say groundwater, we refer to water in the zone of saturation. What do we mean by zone of saturation? I mean, we can have first, you have the ground surface. Below the ground surface, you have the zone, the unsaturated zone, in which you have soil moisture. It is not saturated, meaning the voids, the spaces between the soil matrix, the soil particles, are not completely filled with water. But it has some amount of water, that have smeared the soil particles or the soil matrix. But the voids, you still have air and then you have some water. So that is the unsaturated zone. And then when you go deeper down, that is when you reach the saturated zone. The saturated zone has water filling all the void spaces. All the spaces between, the soil particles are filled with water. So that is the saturated zone. So when we say groundwater, we refer to water in the zone of saturation. We'll expatiate this with some good figures that I will explain, that I will show later. Okay, and then when subsurface water, here are all waters that occur below the earth's surface. Okay, when we say subsurface water, we mean all waters that occur below the earth's surface, meaning it can refer to groundwater as well as water in the unsaturated zone. Okay, and then we have subsurface flow. Okay, subsurface flow is meant to indicate water moving in the zones of aeration and saturation and the deep percolation. So it is generally referring to all flow that is beneath or below the earth's surface. Okay, because the zone of aeration is still called the zone of unsaturation. Okay, because aeration means you have air. Once you have air, it means the space is not completely filled with water. So that is also called unsaturated zone. Okay. And then you have hydrogeology. Hydrogeology covers the study of subsurface water in all its phases. The origin, manner of deposition, that is the manner in which water is deposited, and then the laws of motion guiding the flow of the groundwater or the subsurface water, and then the distribution, including physical and chemical properties, as well as interrelationship with atmospheric and subsurface waters. Other things related to hydrogeology is the effects of human activities and economic values, etc. So generally, hydrogeology is the very, very broad subject that covers almost anything to do with subsurface water. Okay, anything to do with surface water in terms of quantity and even quality. Okay, so hydrogeology basically can be looked at science. Okay, but then civil engineers also go into hydrogeology because when it concerns the quantification, when it comes to the real modeling of the groundwater flow, then that you need a civil engineer. The hydrogeologist knows the properties of the soil, of the rocks, so much. Okay, the science behind the deposition of the water, the manner, and the properties and what have you. While the engineer is concerned with the flow, the modeling, and the design of systems that will utilize the groundwater flow and what have you. So the hydrogeologist and the civil engineer, they work hand in hand in these regards. Okay? And then, yeah, of course, going down to the civil engineers, which are more concerned about the movement and distribution of groundwater and its application. Because engineers are also scientists, but they are called applied scientists. Okay? That's why, like, even when you graduate, your degree reads BS, Bachelor of Science. Of course, some universities do award what they call Bachelor of Engineering. Okay? But basically, engineering is also science or applied science. Okay, engineers are applied scientists. Okay, that's why you have Bachelor of Science, Master of Science, and all that. Did we? Let me check this. Okay, now it shows the next slide. All right, now the porous media, PM. Porous media here, we are referring to the soils and rocks, okay? The earth. Porous media here, we are just referring to the earth, okay? The earth is made up of either soils or rocks. Of course, you have other things, okay? Because the porous media can hold water, it can hold air, it can hold dissolved solids, it can hold chemical pollutants like dissolved and heavy metals and hydrocarbons. Hydrocarbons are basically products from, let's say, oil, okay? Oil related, crude oil related byproducts or products, okay? In addition, you also have pathogens, okay? Pathogens, bacteria, and viruses. The soil we have, it has bacteria, it has viruses, okay? But when we say porous media, basically we are referring to the soils and rocks, but bear it at the back of your mind that it has these components. Some may have all, some may have, but it must have some part of this. For instance, soil always has what is called moisture content. That is the amount of water that is attached to the soil matrix, to the porous media, to the soil grains. Okay, so that is the soil moisture. Okay, called or quantified in form of what is called moisture content. Okay, as well as the soil bacteria, because all these are needed for plant growth, the moisture and all that. Okay. Now, classification of subsurface water. I have started explaining, the different classification of the subsurface water, this is based on Menzel's classification and modifications suggested by Davis and DeWest. Okay. So we have the first figure, which is the common classification. Okay. We have the zone of aeration, or generally you have two. You have the zone of rock fracture, okay, and zone of rock flowage, okay. Zone of rock, when I touch now is not okay. Let me, the problem, okay. Then let me take it to the presentation mode now. Can you see the slide?
We see it, but not in the presentation mode, in the normal mode.
No, in the presentation mode now. I'm using the presentation mode now.
It's still stuck on the first one, I think. We can see the slide, but not in the mode, in the presentation mode.
Okay. What about now? When I write, do you see what I write?
No.
Okay, no, then let me. Page 5. Okay, let me put the presentation from the beginning. Okay, now I'm using the presentation mode from the beginning. Can you see?
It's still on. It shows the slide, but in the normal mode. It's not in the presentation mode for us.
Up till now?
Yeah.
All right, let me quickly go back to, but I want to be writing and all right, let me manage and see how far. All right, so I'm okay, let me see what you asked. Okay, on slide 5, right? Okay. So you have the zone of aeration called the Vedas zone. Vedas, okay? Vedas means you have air, okay? Zone of aeration. Vedas zone contains soil water, which is the immediate zone below the earth surface, just beneath the topsoil, okay? Where you have the soil moisture, where water is not saturated, okay? Sorry, where the soil is not saturated, you still have soil moisture, but it is not saturated. You have the root zone. Yes, what are you saying?
Doctor,
Okay.
can you check if you like you have the home insert and design in the PowerPoint, but and then you have a section that says pins. If you click on that, I think you can be able to draw on the screen.
What?
On the top on the top line, I think on in PowerPoint, you have home
Okay.
section insert and you have pins. Can you click on pins?
Oh, pens. Yeah.
I think now you can write on the screen.
Okay. Yes. Yes.
I'm not missing.
Yes. I can see that. So at least that will help me to be writing, not in the presentation mode. Let me see. But it's still moving. Still not writing.
It's doing the same thing. I don't know.
Yeah.
I don't know.
Think in.
Maybe leave it selected on pen instead of select an object on the top left.
Yeah, it's here, and I selected it. Okay. After all. Oh,
I
okay.
don't know why it
Let
is
me
doing
see.
that.
Yeah. Let me see. So to share. Okay. I know what to do. Let me stop sharing and then share again. Yeah. Probably it may solve the problem. Let me see. Can you now see the presentation mode?
No, it's the same thing.
Okay, let me manage to see what will happen so that we don't lose this time also. All right, so I'm still explaining the soil water. You have gravitational water, which flows under gravity. And then below that, you have capillary water. Capillary water is the initial part of the saturated zone. Okay, water is saturated there, but it's held under negative pressure, okay, suction. It is tight. It is very, very, the water is so much attached to the soil matrix such that water is not even available to wells. Then just below it, the capillary water, I mean, the depth of the capillary water is very, very small, few centimeters, like that. Okay, so there you have the force of attraction between water and soil grains to be very, very high. Okay, despite the fact that water is also saturated in the capillary zone. Okay, but not available for flow. It will not flow when you sink a well. Water from the capillary zone will not flow into your well because of the fact that the water is held tightly together. I mean, between the water and the soil grains. Okay, the water is held tightly by the soil matrix. and then the next you have the groundwater. Okay, and then when you go deeper down, you have what is called the internal water. Okay, and the suggested classification here, you have the intermediate or verdouse zone. Okay, and you have the water table. The water table is like the surface of a river or surface of a stream and all that. So that is the surface of the groundwater. Okay, surface of the groundwater. Okay, the surface of the groundwater, and then you have the phreatic zone. The phreatic zone is where you have the groundwater. The phreatic is simply groundwater. Okay, the phreatic water. Okay, so here you and also is the saturated zone. Okay, the saturated zone, and here you have interstitial water, which is the water between in the in the subsurface. Okay, or between the unsaturated and the saturated zone. And then you have water in unconnected pores. Okay, that is because when you go deeper down, you may have rock formation. Some of the rock formation, they may have spaces or holes or pores that are not connected. And then when you go deeper down, you have water only in chemical combination with rock. Yeah. So let me move to zones of, still on the zones of porous media. So here we'll take each of the zones and explain in greater detail to tell you about the properties, what is found there and what is found. The verdouse zone, which is the first zone, okay, also called unsaturated zone, contains soil moisture, and Richard's equation is often used to mathematically model the movement of water in the unsaturated zone. Okay, so like I said, this is the zone where you find crops, plants, plant roots, where they get their moisture, because moisture is very important for plant growth. Okay, so here you have the soil water, and you have the intermediate verdouse zone. Okay, and you have the fringe water or the capillary fringe. So the capillary fringe here, water pressure is less than atmospheric pressure. So we can say it is under suction or tension or negative, negative pressure. We are going to explain in detail. Okay, if we take the atmospheric pressure as the reference pressure, so above it you have gauge pressure, which is the pressure when you want to find the pressure in your tire. Okay, you use the gauge. The gauge shows pressure above atmospheric. That is, if it is in the atmosphere, when you bring your tire gauge, it will read 0 because it is using the atmospheric pressure as the reference pressure. So atmospheric pressure is now considered as 0. Above atmospheric pressure is now gauge. Below atmospheric pressure is considered vacuum pressure. Okay, or negative. So that's why here water in the capillary fringe is below atmospheric pressure. We say is negative. So vacuum pressure, as we are going to explain in chapter 3, we use it negative gauge, or we just call it vacuum pressure, which is the pressure below atmospheric pressure. So here water is under suction, tension. So it is held tightly to the soil matrix. Okay, and like I said, here it is also almost saturated. It is almost saturated, and water is held by surface tension and capillary forces. Okay, water is held by surface tension and capillary forces. We will explain the capillary. Did I explain capillarity? Yeah, I explained surface tension. Yeah, we did in fluid mechanics. Yeah, so I'm mixing the two up. Yeah, this we already did in fluid mechanics. We explain what is surface tension, capillary effect and all that. So you shouldn't have any problem here. And water is not available to wells. This I explained, because they are tight. The water molecules are tightly held to the soil veins, so it doesn't flow freely. Okay, and it may vary from 2.5 centimeter for fine grain to 200 centimeter for silt. So meaning the smaller the soil particles, the higher the capillary, or the higher the capillary fringe. Yeah, the smaller the slopes, the higher the capillary fringe. And it is just, and moisture content decreases with height. Okay, the moisture content, in this case, it decreases with height, meaning as you go up, the moisture content is decreasing. As you go down, the moisture content increases. We go to the next slide. Still on the zones of porous media, we are discussing the phreatic surface, okay, which is the water table. Okay, water table. Here, if you look at these figures, okay, the first one is showing the unsaturated zone, in which you have, let's say we represent the water molecules with blue color. Okay, so in the unsaturated zone, you have some water particles surrounding the soil grains, and that's why it's saturated. You have some of the void spaces that are empty per se, empty in the sense that it does not they do not contain water, but they contain air. Okay, and then you have the capillary fringe, which is almost saturated with water, and then you have the saturated zone where you have the groundwater flow, which is fully saturated with water. Okay, and in the next figure, the figure on the right hand side, you can see that when you see where water will be available only from the water table deeper down. Okay, water in the capillary fringe will not flow into your well because the water molecules are tied, are held tightly together by surface tension forces and capillary forces. Okay, so here, pore water pressure is equal to atmospheric pressure. Okay, so pressure head is 0. So the pore water pressure at the water surface, here we are referring to the water surface. Okay, the pore water pressure, because atmospheric pressure is what is acting, like when you sink a well, you have atmospheric pressure acting directly on the water surface. The pore water pressure is equal to atmospheric pressure. Okay, so here pressure head is 0. Pressure head is the rise of water when you, we already explained this also in details in fluid mechanics, okay, what pressure head is. So in this case, pressure head is 0, but we are going to explain this in greater detail to see at some points the pressure is not necessarily 0 throughout, okay. It sometimes depends on overlying structures, on whether you have confined aquifer or unconfined aquifer and all that. Okay, this will expatiate more in the subsequent slides. And normally, the water table coincides, the phreatic surface coincides with the water table, and slope gives direction of groundwater movement in an unconfined aquifer. Okay, the slope, I mean, because I still can't. Still testing.
Victor, what if you click on where it says select objects? Maybe it will deselect it or something.
I didn't click it. Okay, slideshow. Resume slideshow. Let me. Okay. The select object is still not deselected.
Yeah. It should let you
Remains
guys
permanently. Yeah, it
decide.
remains permanently on the select object.
Yeah.
All right, let's manage to see what we can have, but it's unfortunate. Otherwise, I can upload it, but we have a few more minutes. Okay, let's see. Maybe next time I will just upload the slide, and then use the Blackboard. Okay, not to just share the screen. So what am I saying? Slope gives direction of groundwater movement. That is, slope of the water surface, because it is not horizontal. Definitely, it's not just horizontal. So it slopes downward depending on orientation. We are going to see later. Okay, so that slope, the movement in an unconfined aquifer. Later we'll explore this aquifer. Aquifer is just geological formation okay, that stores water. Okay, just the rocks, the solid matrix. Okay, that is an aquifer. But an aquifer, we call it aquifer because it yields significant amount of water to wells. If it doesn't yield significant amount of water to wells, we give it names. We have aquiclude, aquifoot, and what have you. But aquifer is simply, the porous media. Okay, porous media that stores water and gives significant amount of water to wells. Okay. Now, types of terrestrial water. Yeah, you have, when you have precipitation, you have surface water, you have groundwater, you have the soil moisture. Okay, so you have, the capillary fringe and the saturated zone below the water table. And surface water versus groundwater. Okay, surface water versus groundwater. In terms of quantity, which one do you think is higher? First, surface water or groundwater?
Groundwater, I think.
Groundwater is we have more water than we have surface water.
No, surface water, yeah, because of oceans and seas.
Yeah, you have the figure there. Saline water in oceans constitute 97.2%. And then you have in ice caps and glaciers 2.2%. Then groundwater is just 0.6%. Of course, groundwater is higher when you consider fresh water. That is water that is not saline, that is not salt water. So when you consider fresh water, that is water in rivers, streams, and lakes, and water, that is termed as groundwater. So in case groundwater constitute about 19%. Okay, it's very high. That is considering fresh water alone. But when you consider the totality of water on the planet Earth, groundwater constitute only 0.61%. Okay, but when you consider water, that is when groundwater is higher in quantity. Do you understand?
Yeah.
Now, again, in terms of quality, which one do you think is having higher quality between surface and groundwater?
Quality in terms of what?
Yeah, quality. Water quality. Will you drink water in the gutter? No, because it has low quality, isn't it? Correct?
Yeah.
Even water from your taps, you have, raw water. The water used to perform ablution. You don't normally drink it because it has lower quality. It is saline. You feel, the taste. It has, it is saline. So you need to use, sweet water for drinking, sometimes even for bathing and what have you. Okay. So normally groundwater is having higher quality than surface water, but of course, because the surface water, like in streams and rivers, is exposed to the atmosphere. So sometimes due to natural or even human activities, some artificial activities can introduce a lot of pollution to the surface water. Of course, water can be contaminated, it can be polluted due to human activities. We dug the ground, we put our underground storage tanks in the fuel stations, isn't it? Sometimes these underground storage tanks, they can leak fuel, and this fuel can penetrate, can infiltrate, can get deeper to join the groundwater table. So groundwater table also is susceptible to contamination, but more often than not, it is usually it usually has higher quality than surface water. And then in terms of sustainability, okay, sustainability here how dependable is groundwater or surface water? Which one can be used, let's say, for so long without exhausting the source of supply? Of course, here in Saudi Arabia, you have, the surface water resources is very poor, if not zero, but it has huge unsustainable groundwater supply. Like I told you, 50% of the water supply or of the water demand is met by the groundwater portion. Okay, so surface water water is sustainable, but groundwater is also highly sustainable. But like I said, when pumping so much from groundwater over time, the quality tends to degrade because of what we call sometimes seawater intrusion or saltwater intrusion. This we will learn in the next chapter, that is chapter 6. We will understand the saltwater intrusion. But groundwater is highly sustainable. Okay, and then about contamination. Okay, contamination is also part of the quality, and then exploration. Groundwater, I mean, and surface water. For surface water, sometimes you need to create dams, to create like a reservoir. Okay, depending on the source of supply, because normally you have rivers flowing and streams, so you like create a dam so that you create a reservoir upstream to like store the water, and then use your pump to be pumping to treatment plants. The same thing for groundwater. You need to dig boreholes, okay, deep wells. Yeah, so that area you may need to dig sometimes up to 1 kilometer, okay, to get groundwater. I told you half about is supplied by about 14 wells, about 1 kilometer on the Riyadh Road. Okay. Now, water-bearing formations. Yeah, I started explaining aquifers. They are simply water-bearing formations because they contain water. Okay, when you go deep down, when you go to the saturated zone, so that zone is not just water. Do you understand? It's not like a river. When you have a river, when you dive into the water, all you have is water, isn't it? 100%. But in form of for groundwater, when you go deep down to the saturated zone, you have water as well as the soil matrix. Okay, is it rock, is it soil, and what have you, whether consolidated or unconsolidated? Is that clear? So the soil matrix or the porous media in the saturated zone is what we refer to the porous media. It's what we call aquifers. Okay, but they have to be able to allow the flow of appreciable amount of water to wells. Okay, so aquifers are formations that can yield significant quantities of water. Okay, this characteristic is imparted by to the formations by interconnected openings or pores through which water can move. Okay, let's say you have sandstone, it's a very good aquifer. When you have clay, clay doesn't allow water to just easily flow, although it has high porosity, but its openings are not so much interconnected. Okay, so for good aquifer, aquifer, it has to have interconnected openings. You have alluvial deposits, which are the best form of aquifers. Probably 90% of all developed aquifers are in such formations. By formation here, we mean simply the solid matrix, okay? The porous media. Is that clear? That is what we mean here by formation, okay? Which is deposited over time due to some geological, events taking place, deposition, and a lot of things. Rock formations of a volcanic nature, limestone and sandstone possess cracks, fissures, cavities, faults, caverns, and joints through which they yield water. All these names are different names to indicate or to tell you the space between or within a rock. Okay, cracks, fissures, cavities, faults, caverns, and joints. Okay, so all these are the spaces within a rock that become interconnected and that allow movement of water within rocks. Okay, my time is up. Okay, so any question?
No, thank you, Doctor.
All right. If you don't have any question till we see today, we will take our second piece and then we will take our second lab as well. So see you all. Bye-bye.